Okay guys, so this video is the continuation of lecture 20, and we went through the theory on how to solve a linear system of first order ODEs. Okay, so let's do an example here. So example, let us say that we have, so dy1 dt will be our first ODE. Function of t is equal to minus 3y1 of t plus y2 of t. Okay, so y1, y2 at what we call the state variables, and the second ODE would be dy2 dt of t is equal to y1 of t minus 3 y2 of t. Okay, and we need to define some initial conditions. So with initial conditions, y1 of 0 equal to 2. Do you remember that one of the initial condition must be non-homogeneous, so different than 0? So that will be the one, and the other one can be homogeneous. Okay, so that we can find a solution. Okay, so we did check that these equations are linear, okay, and that we have a one non-homogeneous solution. So that means that we can attempt to find an analytical solution for this system of ODEs where the number of equations is 2. So first thing, because it's easier, let's just rewrite the above equation in vector form. So expressing the ODEs system in vector form, what do we have? We're going to have y of t equal to so this will be the matrix A times the y of t, okay? Where y of t in this case is equal to what? I mean, we don't need to do this, but d11 dt, dy2 dt. A would be the important matrix over here. For us would be what? These coefficients, which is what? Constant coefficients, minus 3, 1, 1, minus 3. Okay? And then our variables y of t, actually which one? y1 of t and y2 of t. Okay. Page 146. Alright, so let's go through the procedure. What is the first thing we needed to do? One was to assume solutions. Okay, and we say you assume the solution to always be of the form y of t equal to x e and the t. Okay, step 2, we need to go and substitute into ODE's system. That's too much orange. Maybe I'm gonna go back to black. All right. So let's second maybe this. Okay, so in our case, the ODEs of the form equal A of y of t. So we substitute the solution. Okay, we take the derivative of this one. What do we get? Lambda x e lambda t will be equal to what? A x e lambda t. So here you see right away that we could cancel this, the exponential on each side. All right, so that at the end we end up with the I'm going to do this in two steps. You need to do this, but you end up basically with the expression A x equal to lambda x, which is the definition of an eigenvalue problem. Okay, so now that means that from here you can go and rewrite this as A minus lambda. Okay, and if we use the identity matrix, okay, we have this equals 0. Okay, remember this is just to show that we need to take the diagonals. Okay, so now we say that this equation has solutions in two cases, either x equal to 0, which yields to the trivial solution, or this term over here is equal to 0, which means that the determinant of A minus lambda times the identity matrix equal to 0. So equation satisfied if and only if we have either one of these two conditions. Okay, so we know the trivial solution is not of interest for us. We want to care about this one. So this equation here is going to yield to what we know as the characteristic equation. So let's do that. So basically I think step 3 was to solve characteristic equation which should give us the eigenvalues, basically the lambdas. Alright, so let's rewrite that equation. We have determinant of the matrix A that we say is equal to -3, 1, 1, -3. Alright, and now we have minus lambda of 1, 0, 0, 1. Equal to 0. So this actually gives determinant of -3 minus lambda, 1, -3 minus lambda, and 1. So again, this will give us the equation of -3 minus lambda times -3 minus lambda minus 1 times 1. So if we expand this, let me do that on the next page. So if we expand that equation, we get 9 plus 3 lambda plus 3 lambda plus lambda squared minus 1 equal to 0, or lambda squared plus 6 lambda plus 8 equal to 0. Okay, and this is the characteristic equation. So as you can see, it's a quadratic equation, so it's second order, so we need two roots, okay? So if we solve for the eigenvalues, what do we get? We're gonna get here that the roots of that equation actually going to be equal the eigenvalues, so lambda 1, 2 will be equal to what? Minus b, which is -6, plus minus 6 squared minus 4 of 1 and 8, and this is the square root divided by 2a, which is 1. So this is going to give us that so we get two roots, so what do we get? -6. So that's 36 minus 32 is 4, so it's -2, so one of the roots will be -4, the one will be -2. Okay? So it doesn't matter which order you put them, but in general, okay, or generally, the eigenvalues are sorted from max to low. Okay, but it really doesn't matter. Okay. Okay, so in our case, then we're going to say that, so our maximum will be which one? -2, and our minimum here is -4. Okay, so this will be our two eigenvalues. All right, now that we have the eigenvalues, what do we need to do? Do you remember? We did recognize, because the equation was of this form, that we needed to solve an eigenvalue-eigenvector problem. So we did a half of it. We solved the eigenvalue. So now we need to solve for the eigenvectors. So that is step 4. So solve or find the eigenvectors. Okay, so for that, we do it for each one of the eigenvalues. So let's say initially our first value we're going to take is lambda 1. And what we need to go is go back and substitute into our initial equation, which is this one over here. Okay, equal to 0. So if we substitute into that equation, what do we get? We're going to get minus 3 minus lambda 1 was equal to what? Minus 2. So we get minus 2. Okay. Then we get here the 1 value that we had. 1. And on this side we're going to get the same thing. Minus 3 minus 2. And then we have here now x1, x2. And to make sure that we know this is for the first value, we're going to add here a little 1. And this must be equal to 0. So this is just going to give us at the end that, so minus 3 plus 2 will be minus 1, 1, 1 minus 1 of x1, x2 to the 1 will be equal to 0. Alright? Okay. So now, this equation again, when is this equation satisfied? Either you have x1 x2 equal to 0, which will be what? The trivial solution that we're not interested, or then the other way will be to have the system, to solve the system, minus x1 plus x2 equal to 0, and x1 minus x2 equal to 0. So basically here, mathematically, what do you see? That this is the same equation. Okay, basically if you have x will be equal to what? To x1 equal x2. So it will give you x2 minus x2 will equal to 0. Or x2 will be equal to x1. You have minus x1 plus x2 equal x1. So you have minus x1 plus x1 will be equal to 0. Okay, so that means that for any value of, as long as they equal x1 and x2, you can have an infinite number of solutions. Okay, so here shows an infinite number of solutions, but that was expected. If you remember, I told you that the eigenvector eigenvalue problem is a very useful mathematical tool for engineering problems, but the real mathematical meaning is just like if you have a vector. Okay, you know a vector has a direction and a magnitude. So there's an infinite number of vectors that will give you the direction. Okay, so as long as they understand direction, that vector is a solution. So basically that is what happens with the eigenvector eigenvalue problem, is that it's just giving you directions and no magnitude. So there's an infinite number of solutions. So that means that you can actually pick any one of those vectors that give you the direction, and that's what you do in order to find the eigenvector. So this will be page 147. So for instance, let's just say fix 1, and let's say we're going to fix x1 to 1. Then what happened? I mean, you can go to either equation, but if x1 equal to 1, that would mean that x2 will also be equal to 1. Okay? Out of that equation, x1 equal to 1, this will be equal here to 0. So minus 1 plus 1, 0, 1 minus 1, 0, in order to be satisfied. So x2 equal to 1. So it's that simple. So that means that the first eigenvector will just be equal to 1, 1. But again, you should have an infinite. 2, 2 will be 1, half will be 1, 0.25, 0.25, whatever number you want will always be a solution. So here we have our first eigenvector corresponding to the eigenvalue lambda 1. So now we do exactly the same thing for the second one. So if lambda equal lambda 2, we need to go back and substitute into this equation, into the equation that yield to the characteristic equation. Alright? So this will give us what? Can go a little bit faster now. This will yield to minus 3, 1, 1, minus 3, minus the identity matrix 1, 0, 0. Oops. Lambda of x will be equal to 0, which this is just going to give us that minus 3 minus the second value was minus 4, 1, 1, minus 3 minus 4 of, let's expand this, x1, x2 equal to 0. So at the end we have the equation minus 3, so this will be plus 4, 1, 1, 1, 1, x1, x2 equal to 0. Okay, and to make sure that we solve, that we know this is for the second eigenvector, we compare here too. So again, we go again through the same routine. This equation is satisfied under which cases? So satisfied if and only if. I read under this form. We have the first case x1, x2 of 2 equal to 0, which we know is a trivial solution, which is not of interest to us. The other one is that here you can have the system x1 plus x2 equal to 0, x1 plus x2 equal to 0. So again, you see there's infinite number of solutions. Same reason as before, is because the eigenvectors, you're only interested about the direction and not the magnitude. So let's say we fix 1. Let's say x1 equal to 1. In that case, x2 equal to minus 1. So the second eigenvector will be what? x1, x2 of 2 is equal to 1 minus 1. Okay. All right, almost there. Page 149. So the next step is to do what? So next step will be step 5. So now we need to go and substitute back into the assumed solution. So substitute into assume solution. So what was the assumed solution? If you remember, the assumed solution is y of t equal to x, the eigenvector, e of lambda t, the eigenvalue. Okay? So this will mean that y of t vector here will be equal to what? C1 times the first eigenvector 1, 1 exponential of minus 2t plus C2 1 minus 1, the second eigenvector of exponential of minus 4t. Alright. So this would be the general solution. Okay? I mean, I don't need to put it, but maybe I should have done one step up, and it would be this is equal to what? C1 of x1 exponential of lambda 1t plus C2 second eigenvector e lambda 2t. Okay? So this is the general solution. So in order to find the particular solution, what we need to do is to solve for the coefficients C1 and C2 that are obtained for the initial conditions. So that would be basically almost the last step. So 6 will be solve for C1, C2 using initial conditions. So the two initial conditions for these problems were initial conditions. If you remember, one is to be non-homogeneous, which was the first one, but the second one was homogeneous. So we have this. So if we just substitute over here, what do we get? So we substitute over here. So substitute into general solution. And what do we get is what? So let's do the first one. We're going to get 2. Okay, y of 0 will be equal to what? So we'll do the first one. This will be for the top one. Okay, this is y1. The top one, this will be y2. So it will be c1 e to the 0 plus c2 e to the 0. Okay, and this one, the second one will be 0 will be equal to c1 e to the 0, because it will be this one, minus c2 e to the 0. So this will give us a system of c1 plus c2 equal to 2, and c1 minus c2 equal to 0. Okay, so over here you can see right away that c2, c1 will be equal to c2, and that both will be equal to 1. Okay, so now finally the last step will be to substitute C1 and C2 into general solution. So what you're going to get is y of t, which is equal to y1 of t, y2 of t, will be equal to what? So C1 is 1, so it will just be 1, 1 exponential of minus 2t plus 1 minus 1 exponential of minus 4t. Okay, and this is now the particular solution. Okay, so I'm going to stop here this video because I don't want to make them way too long, but basically the next one should be a lot shorter, and the only thing I'm going to do is to show you basically how to plot this in MATLAB, and obviously the whole goal is to how to solve this equation numerically. So I will tell you and probably show you my code on how to solve this using MATLAB, and how to plot the exact solution so that we can compare it with the numerical solutions. Okay, so thank you for your attention.